Hello there. In this lesson, we're going to learn about LeChateliers Principle. LeChateliers Principle refers to the changes that equilibrium will undergo when a stress is applied externally. For example, you may have seen this in class where we have these two tubes that are filled with gases at equilibrium. The one gas is NO2, which has that brown color. You can see brownish color in both of the tubes. And the other gas is colorless. And you can see there's a different composition of those gases depending on the temperature. The one on the left here is in ice bath, and the other one on the right is in some hot water. And so there is obviously a shift going on where we're pushing the reaction either to the left or to the right, depending on the temperature. So there are a bunch of stresses like temperature that you can apply to an equilibrium, and the equilibrium will shift in order to compensate. And so we're going to learn about that compensation today. And the overriding way of keeping all this organized is called LeChateliers Principle, and we'll point out how it affects each of these stresses. All right, so there's three different stresses that we're going to look at today. One is we're going to change concentration of particular components, whether they're on the right-hand side or the left-hand side of the equilibrium arrow. You can add or remove them in various ways, and that will alter the composition of the components at equilibrium. The second is if you have a gaseous reactant as part of your equilibrium, you could change the volume and hence the pressure of those gaseous components by squeezing the gases into a smaller volume or let them expand into a larger volume, and that also influences the composition at equilibrium. And the last one is going to be the one that we alluded to at the beginning there, which is changing the temperature. So the basic premise that is summarized with LeChateliers Principle is if you do any of those external stresses that are listed above here, that the system, the equilibrium system, is going to adjust in a way that opposes whatever change you made. So opposing the change is what's going to happen. And so that's a way of keeping track or predicting what's happening in an equilibrium system. And so LeChateliers Principle is very useful for that. But we're also going to go into why it happens. And the why isn't that the reaction feels like going one way or another. Of course, there's got to be some physical characteristics that are causing it to shift left or right, and we're going to look at what those will be. Okay, so the first one we're going to look at is a change in concentration. So this type of stress is where you're either adding something or removing something. And to follow LeChateliers Principle, the equilibrium will shift in the direction that opposes the change, right? So if we added something, it's going to go in the direction that uses up whatever was added. And if you remove something, it's going to go in the direction that replenishes what was taken away. So in the example we have here in the side, we've got the good old Haber process there, making ammonia. And we're starting off at an equilibrium, right? It's at the beginning here, everything's constant. And then we're going to add some nitrogen, right? So there's a spike there where the nitrogen was added in. And then the equilibrium is going to shift in the direction that opposes that. So if we add nitrogen, it's going to go in the direction that reduces the nitrogen, and that would be to the right. So that means the nitrogen is going to decrease until it gets back to a new equilibrium. And also, because hydrogen is on the same side as the nitrogen, it's also going to decrease until you get to a new equilibrium. And then, of course, because the reaction is going to the right, the ammonia is going to increase, and you'll end up with a new equilibrium there. So that is the overall effect of opposing the change for that situation. The reason why is down to kinetics, right? If you increase the concentration of nitrogen here, that is going to increase the rate of reaction that consumes nitrogen, right? The rates of reaction are due to the concentration and the frequency of those collisions. And the reverse reaction we didn't change anything about, so it would stay the same. So you got an increase in the forward reaction. The reverse reaction had no change, and so overall this is going to shift to the right to compensate for that added nitrogen. So if you're going to explain why, it's got to include those concentration changes. Now, just as a reminder, the concentration changes only work for things with the variable concentration. So it doesn't work for things that are solid or liquid, only things that are gases or aqueous components will be affected. So if you remove some CO2, this is going to decrease the amount of CO2, and the reaction will therefore shift in the direction that increases CO2, which means to the right. If you add some more of this Fe2O3, that's a solid, so you can add as much of that as you like, and as long as you don't mess with the concentrations of the gases, you'll find there's no change. And finally, if we remove some carbon monoxide here, we decrease the amount of that, well, the reaction is going to shift due to a decrease in this reaction rate, right? So the rate of reaction to the left is going to be larger than the one to the right, and you will see that this reaction will shift to the left and end up producing a new equilibrium that's shifted that direction. Stresses can even be represented on an ice table by putting in an extra line. So it becomes an ice table. Anyway, so we have this theoretical equilibrium going on here with an equilibrium constant of 2, right? You've got twice as much on the right side as you do on the left. And then we're going to monkey it up, stress it out by adding some extra of compound A. And so the shift is going to go in the direction that decreases compound A, so you're going to lose X amount from there, and you're going to gain X amount on the other side. And then you could solve for those quantities by inputting this into your equilibrium expression. So it would be 0.3 in total there minus X for equilibrium of the new state, and 0.4 plus the X on the other side. So you can put that into our expression. Our K is going to be the concentration of B over A. The constant is 2. The concentration of B is 0.4 plus X. And the concentration of A is 0.3 minus X. And then we can move some things around here. So 2 times 0.3 minus X equals 0.4 plus X. And we'll go up here to finish this off. So this would be 0.6 minus 2x equals 0.4 plus x. And we'll group some things together here. So we got 0.6 minus 0.4 equals x plus 2x. So that takes us to 3x over here and 0.2 on the other side. And then we're going to divide both these by 3. And we get x equals 0.2 divided by 3. That'd be like 0.066 moles per liter. So then we can plug that back up here. So 0.3 minus the 0.66 would be a final, let's use a different color. This would be 0.233, and or 4, I guess. And over here we got the 0.4 plus the 0.66, so that'd be that 466 as a concentration when you're done. Alrighty, stress number 2 involves changing the volume and hence the pressure of an equilibrium that includes gases, right? So the same equilibrium is all gases. And what happens according to LeChateliers Principle is that any change to the pressure, if the equilibrium could shift and oppose that change, it will. So for instance, if we decrease the volume, as mentioned here, that's going to increase the pressure. And LeChateliers Principle tells us it's going to shift to oppose that change. So if increased pressure is the stress, then the shift should decrease the pressure. And it does that by shifting to the side with fewer particles. So if we add up the particles here, we've got 4 total particles on the left-hand side and 2 on the right. So if you want to decrease the pressure inside that system, it's going to shift to the right. Now, of course, that doesn't explain why. So the explanation of why then would be that the effect of changing the volume changes the concentrations of the side with more reacting particles more. All these quantities become the exponents, as you recall, and so the concentrations of those are going to increase and decrease to a greater degree than when the values are smaller. So let's have a look at Q here just to illustrate that. for our starting amount here, we've got 3 values. Actually, I'm going to input these. So I inputted the concentrations right off the graph here. 0.2 for the ammonia on the top, squared. 0.3 for the hydrogen on the bottom, cubed. And 0.1 for the nitrogen on the bottom, to the power of 1. And when I calculate that, it comes out to 14.8 for the constant. So let's see what happens when the volume is doubled. When the volume is doubled, the concentration of all those things is going to drop to half of what it was. So 0.2 is going to become 0.1, and that'll be squared. The 0.3 will become 0.15, and that'll be cubed. And the 0.1 becomes 0.05, and that'll be to the power of 1. So let's see what that comes out to be. So that comes out to 59.3. And so you can see that Q is much, much larger than K, and that means the equilibrium is going to shift to the left, which is what we'd expect with LeChateliers principle, right? LeChateliers principle said that if we double the volume here, that's going to cause a drop in the concentration or pressure, and that means the equilibrium should shift in the direction that increases pressure, and so the concentrations bear that out. On the graph, it would kind of look like this. If you doubled the volume, all these values are going to drop by a half, right? This would drop way down here. This is dropped down to, I'll leave a little space here, to 1.5 there. And then it's going to shift to the side with the nitrogen and the hydrogen. So the hydrogen's going to spike back up here. And the nitrogen as well, just a little slower because it has a different coefficient. And the ammonia, which is down here, would decrease further down to about there. So you get a new equilibrium as the result of that change in volume. So our final stress is that of applying a change in temperature. And so we return to our old friends, nitrogen dioxide and the N2O4. And you can see that in the cold, that the equilibrium has shifted in the direction that produced more of this colorless gas. And so that is opposing a change. If you are cooling something, it will go in the direction that heats it, which is on the left. And this one is the hot water one. And it's the opposite shift. It's going to go in the direction that cools it, which is to the right. And that produces more of the brown colored gas, which you can see in the tube. To explain why, you have to look at the activation energy for each direction. Added energy is a big boost to the particles that are trying to get over this big activation energy for the forward direction, right? And it's not as big of a boost to the particles going the other way. They don't have as much of an energy hill to climb to go in this direction. And so adding extra energy doesn't speed up that reaction as much as it does for the forward reaction. Now, to be clear, both reactions are going to speed up when you warm up the solution. Just the direction that's endothermic gets a bigger boost and therefore a greater increase in the equilibrium rates of reaction. Alrighty, so let's use what we've learned to make a prediction here. How would the concentrations change when heated? When heated, this reaction is going the direction that absorbs heat, which would be to the left there, which means our NH3 concentration should decrease, and then our hydrogen concentration should increase, and then the nitrogen concentration should increase as well. You have to say it that way. Okay, that's the effect of temperature. Okay, just a little reminder that when you use enthalpy values to express whether or not a reaction is endothermic or exothermic, that positive values like this one mean that the heat quantity is over here on the left, and negative values like this guy means the heat is on the right. And then it says which way will these reactions shift when the temperature is increased. So if you increase this endothermic reaction, it's going to go in the direction that cools it, which is to the right. It'll be the opposite for this one because it'll want to be going in the direction that absorbs the added heat. Now, temperature change is the only one of these three stresses that actually changes the value of the equilibrium constant. So what you can do here is you can see that this shift causes an increase in the concentration on the right-hand side. And so, because K is always, right side over left side, K is going to increase for this situation because it's shifting to the right. And then conversely, if you get an exothermic reaction and you're heating it and it's going to shift it to the left, that means that the left side is going to get greater, the right side is going to get smaller, and the overall value of the constant will decrease. So there you go. Another handy little detail about LeChateliers principle and the shifts that it produces. Finally, we're going to look at a few changes that are going to have no effect on the equilibrium concentrations. First is a catalyst. A catalyst, of course, speeds up the rate of reaction, but it does so in both directions equally. So the forward reaction is increased, but so is the reverse reaction. It might get you to equilibrium a little faster, but it'll be the same equilibrium. The other one is adding an inert gas. An inert gas is just any gas that isn't involved in the reaction itself. And this, of course, would have the effect of keeping or increasing the pressure inside of a fixed volume container. But as long as the volume doesn't change, then the concentrations of all those components will not change either. And so this inert gas just ends up being another partial pressure that's added in there. It will impede the reaction. Kind of think of it like the anti-catalyst. It's going to impede the reactions in both ways because it will interfere with some effective collisions. But again, it has the same effect going both ways, and so no net overall effect to the equilibrium position. All right, hope that helped. I'll see you soon.